Top 10 mind-bending facts about the quantum realm explained simply. Our everyday world operates on a reassuringly predictable set of rules. If you drop a ball, it falls. If you push a door, it opens. But if you shrink down, smaller than an atom, you enter a realm where all the familiar rules of reality shatter into a million bewildering pieces. This is the quantum realm, the fundamental layer of the universe that governs the behavior of subatomic particles. It's a world of pure potential, where particles can be in multiple places at once, teleport through solid walls, and communicate across galaxies instantaneously. To peek into the quantum world is to glimpse the very bedrock of existence, and it's stranger and more wonderful than any science fiction. Here are 10 of its most mind-bending facts, explained simply. 1. Wave-particle duality. Everything is both a wave and a particle. In our world, things are either objects, particles, or waves. A baseball is a particle. The ripples in a pond are waves. Simple. In the quantum realm, however, this distinction dissolves. The tiniest building blocks of reality, like electrons and photons, have a split personality. Sometimes they act like a tiny solid ball, located at a single point in space. At other times, they behave like a spread-out, ethereal wave of energy. The strangest part? Their identity depends on whether you're looking. In the famous double-slit experiment, when scientists don't watch which slit a particle goes through, it acts like a wave and passes through both at once, creating an interference pattern on the other side. But the moment they set up a detector to see which slit it chooses, the particle acts like a well-behaved ball and goes through only one. It's as if reality itself is shy and only reveals its true, wavy nature when it thinks no one is watching. 2. Superposition, the art of being everywhere and nowhere. Before you observe a quantum particle, it doesn't have a definite position or state. Instead, it exists in a fuzzy cloud of all its possible states simultaneously. This is called superposition. An electron isn't at point A or point B. It's in a state of being at both A and B, and everywhere in between, all at once. It's a state of pure maybe. The most famous analogy for this is Schrödinger's cat. Imagine a cat in a sealed box with a device that has a 50-50 chance of killing it based on a random quantum event. Until you open the box to check, the cat isn't alive or dead. According to quantum mechanics, it's in a superposition of both alive and dead. The act of opening the box and observing the system forces it to choose a single reality. Before that moment of observation, the universe allows for all possibilities to coexist. 3. The observer effect. Reality changes when you look at it. This flows directly from superposition and is perhaps the most reality-shattering concept in all of physics. The quantum world doesn't just act weirdly when we're not looking. The very act of looking or measuring it fundamentally changes the outcome. When a particle is in its maybe state of superposition, our observation forces its hand. The cloud of potential realities collapses into a single, definite reality. This isn't like measuring the air pressure in a tire, where your measurement tool has a tiny physical effect. In the quantum realm, the interaction is absolute. It's as if you're trying to discover the true color of a chameleon that instantly changes its color to red every time you shine a light on it. You can know its observed state, but you can never know its true unobserved state, because the act of observation is what creates that state in the first place. This suggests a bizarre link between consciousness or measurement and the nature of reality itself. Quantum entanglement, spooky action at a distance. Imagine you have two coins that are magically linked. You give one to your friend, who travels to the other side of the galaxy. You flip your coin, and it lands on heads. The instant it does, you know with 100% certainty that your friend's coin, light years away, has just landed on tails. This is quantum entanglement. Two or more particles can become linked in such a way that their fates are intertwined, no matter how vast the distance separating them. If you measure a property of one entangled particle, like its spin, you instantly know the corresponding property of its partner. Information seems to travel between them faster than the speed of light, something Albert Einstein famously called spooky action at a distance. This doesn't allow for faster-than-light communication, but it does reveal a deeply mysterious and interconnected property of the universe, suggesting that space as we know it might not be the barrier we think it is. Quantum tunneling. You can literally walk through walls. In our everyday world, if you throw a ball at a solid wall, it will bounce back. It will never, ever pass through it. But in the quantum realm, particles can and do. Quantum tunneling describes a phenomenon where a particle can pass directly through a solid barrier that it shouldn't have enough energy to overcome. It's a game of probabilities. The particle's wave-like nature means its location is spread out, and there's a tiny but non-zero chance that part of its wave will exist on the other side of the barrier. If that happens, the particle can simply appear on the other side without ever breaking a hole in the wall. This isn't just a quirky theory. It's why the sun shines. The fusion that powers our star is only possible because quantum tunneling allows protons to overcome their mutual repulsion and get close enough to fuse together. The Heisenberg uncertainty principle. There's a cosmic limit to knowledge. You can't know everything about a quantum particle at the same time. The Heisenberg uncertainty principle states that there is a fundamental trade-off between knowing certain pairs of properties. The more precisely you measure a particle's position, the less precisely you can know its momentum, its mass times its velocity, and vice versa. Think of it like trying to photograph a moving car. If you use a very fast shutter speed, you get a crystal clear image of the car's exact location, but the static picture tells you nothing about its speed. If you use a slow shutter speed, you get a long, blurry streak that clearly shows the car's direction and speed, but you can't pinpoint its exact location at any given moment. This isn't a limitation of our measuring instruments. It's a fundamental property of the universe. There's a built-in fuzziness to reality that we can never escape. Quantum leaps. Particles are teleporters. When we talk about something making a quantum leap, we usually mean a big, sudden jump. In physics, it's even stranger. When an electron in an atom moves from a lower energy level to a higher one, it doesn't travel through the space in between. It simply disappears from one location and reappears in the other instantaneously. There is no journey. This is the true meaning of a quantum leap. It's not a gradual movement, like climbing a staircase. It's like being on the first floor one moment and the third floor the next, without ever existing on the second floor or the staircase itself. This is another consequence of the wave-particle nature of reality. The allowed energy states for an electron are like fixed train stations, and it can only exist at the stations, not on the tracks between them. Virtual particles. Something is constantly popping out of nothing. According to quantum field theory, empty space is not empty at all. It's a seething, bubbling chaos of energy known as quantum foam. Out of this foam, pairs of virtual particles, a particle and its antiparticle, are constantly popping into existence, only to annihilate each other and disappear again in a tiny fraction of a second. They essentially borrow energy from the universe, allowed by the uncertainty principle, as long as they pay it back before the universe notices. While they are fleeting, these virtual particles are not just a mathematical trick. They have real, measurable effects, such as the Casimir effect, where two uncharged plates placed very close together in a vacuum will be pushed together by the pressure of the virtual particles outside them. The quantum Zeno effect. A watched particle never changes. The old saying, "a watched pot never boils," is literally true in the quantum realm. This bizarre phenomenon, known as the quantum Zeno effect, states that if you observe an unstable quantum system frequently enough, you can prevent it from changing or decaying. Every time you make a measurement, you collapse the particle's wave function back into its initial state, effectively resetting its decay clock to zero. If you could observe it continuously, you could, theoretically, hold it in its initial state forever. It's as if your constant observation freezes the particle in time, preventing it from evolving as it naturally would. This demonstrates yet again the profound and active role the act of measurement plays in shaping quantum reality. 10. The many worlds interpretation. Every possibility creates a new universe. This is less a proven fact and more a mind-blowing theory to explain the weirdness of superposition, but it's too fascinating to ignore. The many worlds interpretation proposes a radical solution to the measurement problem. Why does a particle choose one reality out of all possibilities when we observe it? The theory says it doesn't choose at all. Instead, the universe splits. For every possible outcome, a new parallel universe is created where that outcome becomes reality. So, when Schrödinger's cat is in the box, the universe splits into two, one where the cat lives and one where the cat dies. You just happen to be the version of you that exists in one of those branches. This implies that there is an infinite number of parallel universes, containing every possible version of history and every possible outcome of every choice you've ever made. If your mind is suitably bent and you're eager for more, these books are fantastic and accessible guides to the quantum realm. Something Deeply Hidden: Quantum Worlds and the Emergence of Space-Time by Sean Carroll. How to Teach Quantum Physics to Your Dog by Chad Orzel. A Brief History of Time by Stephen Hawking. The Elegant Universe, Superstrings, Hidden Dimensions, and the Quest for the Ultimate Theory by Brian Greene.